which is defined very similar, is a change in the bulk volume due to a change in pore pressure divided the original bulk volume, also with these two conditions. So those two are definitions, okay? So I haven't done anything new other than define those two. Here is when I'm going to get into some equations to calculate this value based on things that we already know. Okay, so now let's assume that the variation of pore volume is going to be equal to the variation of bulk volume. This is not always true, okay? But what that means is that all the compaction of the rock it goes into loss of porosity. And that's sometimes not true because the minerals can also compress. But this is going to be a convenient assumption, and it actually is not too far from the actual solution unless you get very, very tight porosities. But if we assume this, we can rewrite this equation CPP. So CPP, which is that one over there, is going to be 1 over VP. And I'm going to change now this variation in pore volume is going to be equal to the variation in bulk volume, dPP. And in addition to that, I didn't do anything new, okay? I just changed this one for that one. In addition to that, I'm going to divide here by the bulk volume, and I'm going to divide here by the bulk volume too, which I can do that, right? Because this one divided by this one is equal to 1, so I haven't done any change. But now, as you can see from here, what is this guy? Is that one over there, right? Is the bulk compressibility, as we defined it before. And what about this one? So let me just write the one on top. It's going to be CBP. What is this? You know that? Porosity, very well. Porosity, pore volume divided by bulk volume, that's going to be the porosity. And now we're getting very close to the final equation. What is a compressibility? A compressibility is a measure of the rock to say how soft it is against the action of stresses. And we have seen that, but with another word, and we have been looking at the opposite, which is the stiffness modulus, like the Young modulus. All of those tell us how hard the rock is. But it's just the inverse of the other. So here, CBP is equal to 1 over M, where M, if you remember, is the constraint modulus. So our final equation is going to be that the formation compressibility is 1 divided porosity times the constraint modulus. Do you guys remember what the constraint modulus was? The constraint modulus came from assuming this 1D type of deformation. So the same as over here, this is the constraint modulus, and it's the stiffness coefficient that you need in order to produce a given strain in this direction with stress in the same direction without lateral expansion. It's not the same as the Young modulus. In the homework, you're going to have to compute an example of this constraint modulus. And this is mostly always the case, for a Poisson ratio larger than 0, M is larger than E, it makes sense. You need more stress to achieve the same strain when you do not let the size to expand. So now with this equation, you can calculate what is the formation compressibility. And I have one example in my notes. I like that we have to move on, guys, because I want to talk about tensile strength. But I recommend that you go to the notes and you check here a problem, which is where is that? Not here. Let me get there in a sec. What happened? All right, so we go here, horizontal stresses, stress regimes, no, here. Compressibility, okay? So this is the same thing that we have seen so far, and here you have an example, a worked-out example to compute this value in a micro zip. There is a mistake here. I have to correct this, okay? But there shouldn't be any space. All right, so we have seen the example of compressibility. Let's now talk about a general solution for elasticity problems. So far, these problems of both calculating horizontal stress or calculating compressibility, those are very simple problems because we have assumed a very straightforward deformation, a very simple deformation. And in order to solve those, we need to use the matrix and just replace the strains, and we get the solution right away. But in general, this is not going to be the case, right? Let's say that I have a formation with a lot of fractures and wellbores. All right, so let's say that I'm looking at the formation here, and here there is, and we're looking from the side, there is a fracture over here, and actually there was a wellbore drilled in that direction, and here there is a smaller fracture, and here there is a bigger fracture, and here there is a fracture that also goes like that. And I want to know what is the stress at that location. How are you going to solve that problem? Any suggestions? Something very useful that we can do, as we have done in the other problems, is to understand what are called the boundary conditions, right? So probably here we're going to have a vertical stress in the far field. In this problem, we're going to have horizontal stresses, and probably we may assume in this case that the bottom base is not moving. And then we're a little bit closer to solving the problem, but not quite yet. Before I scare you with the equation that is used to solve this problem, Let's work with another equation that you know much better, which is the fluid flow equation. If you want to solve a fluid flow equation, what equation comes right ahead to your mind? The diffusivity equation, but how do you get to the diffusivity equation? What are the assumptions on that diffusivity equation?
One-dimensional with a single phase flow.
Okay, so what is the relation or the equation that links flow rate with pressure gradient? That's the other one. Let's go with that one. So with mass conservation on a fluid flow problem, mass conservation implies that everything that gets into a volume must get out by another phase. And that mathematically is expressed with the divergence equation. So, but simply, let me tell you what this is. This tells that any variation of fluid in direction 1, let's say the direction 1 is this, if say in this phase you're getting 10 and this phase you're getting 9, that means that in some other direction you need to make up for that. So if here you're injecting 10, probably here you'll get 11 to compensate for that other direction. That's basically the continuity equation. It tells you that the variations in one direction have to be compensated by variations in another direction so that they are zero. So there is mass conservation. Everything that gets out, that gets into a volume, must get out. And that's expressed with these variation terms. There is another very important equation that we need in order to solve this type of fluid flow problems. This one tells us how the fluid is going to go, in which direction it's going to go. But it doesn't tell us how fast. So what else do we need? Darcy's law, okay? So this type of equation is going to allow me to calculate, let me do it with another small fracture so it's clearer, somewhere over there. If I had a pressure front, that pressure front around that fracture is going to be something like this. So this equation allows me to solve those pressure fronts, where this is the lowest, this is the maximum around there. And the gradient of that tells me the direction of the fluid, Q, okay? It tells me the direction, but it doesn't tell me how fast that is. So in order to solve that problem, I need also the Darcy equation. And the Darcy equation, and now we're going to write it in 3 dimensions, is Q1, Q2, and Q3 are equal to K over mu times dp1 dx1. No, there's no dp1. P is in scalar, okay? So dp divided dx1, dp dx2, dp dx3. So this one is called a divergence. How is this one called? I'm missing a sign here. In mathematical terms. This is what is called a gradient. Okay? And with this one now, I can tell what is the magnitude of Q. I knew the direction before, but I didn't know the magnitude. I didn't know how fast the fluid would move into this direction. But now with this equation, I know that. I know the magnitude of that. But basically, my point here is that if you combine these two equations, then you can arrive. So look, this pressure Q is over there, and I can get Q from here, right? So if you combine these two equations, you're going to end up with an equation which is going to look something like this, which is close to the, we need one more step to get to the diffusivity equation to add time, but if we don't add time, it's going to look something like that. The important thing here is not the equation, okay? And I don't want you to remember this by heart, but I like that we understand, how to solve these continuum mechanic problems based on a simpler problem. It's just an equation and involves variations of pressure as a function of space. If you solve this equation, you solve that fluid flow problem that we have over there. And with the mechanics problem, it's going to be very similar, very, very similar, but instead of solving for pressure, we're going to be solving for displacements. And the equation for that, as I told you before, is a little bit scary, okay? But we're going to write it anyways. And you don't have to remember this by heart, but you have to understand what's going on over here. And you have to remember what is important about this. So have you guys seen some of these signs before? In which class, Monsieur Tozer?
I want to say it was either Res2 or maybe Transport. Yeah, definitely Res2.
Okay, those guys are just derivatives, okay? That's all what they are. And they change a little bit, but they are just a derivative. And this is the general solution for a continuum mechanics problem. If you solve this equation, then you can tell what the stress is for those for any arbitrary boundary conditions and variations inside the medium. So if you were to solve this fraction for that problem, you could tell what that stress is, what are the normal stresses, what are the shear stresses, what is everything. Let's try to understand the equation now. First of all, you have what are called the Roc property parameters, in which mu, these actually have a name. These are called the Lamé parameters, and where mu is equal to what we have already seen is the shear modulus, and it's called that one is called the second Lamé parameter. The first Lamé parameter is the combination of Poisson ratios and one modulus. And that depends on the rock, okay? And then you have here U, these are displacements, and that displacement is going to have, remember this is a vector, U1, UT, U2, U3. These are body forces. The most common one is gravity. In problems of sand production, if you have a lot of drag of the fluids in the sand, you may add that term. But this is something that it depends on internal forces. And these guys are just derivatives, okay? But it's very similar to this one, but a little bit more complicated. This one is a divergence. With that one together is a divergence, but these are just derivatives. I'm going to write them down, but you don't have to remember these by heart, guys. Don't worry. And this one is a dot product times this one. This one is a divergence, and This one is what is called a Laplacian. And similar to that equation over there is now you have 2 times, derivative 2 times. But those are just derivatives. And if you have derivatives, what you have here is in order to solve it, this is a differential equation. If you solve the differential equation, then you can solve that problem over there. So the question now is, how do we solve that equation? And there are basically 2 ways of solving this equation. One way would be to solve it analytically. So an analytical solution for the equation. And for that, we're not going to solve it because it takes a lot of work to do that. And actually, people, back in 19th century, even 20th century, they spent a lot of time with integrals and with convolution and other techniques in order to solve problems analytically. And for example, here we're going to use the Kirsch equation, which allows us to predict stresses around wellbores. That's an analytical equation that we're going to see later on. Also, we're going to use later on an equation from a guy called Snedon that's going to allow us to calculate stresses around fractures. Also, analytical equation. And there are a few more, and there are a few more methods here, but we're going to talk about that later on when we get to that. But we're not going to solve the analytical equation, but you should know that these are just solutions for that problem, okay? If we're going to do this with CMG later on, but in general, if you want to solve a general problem of mechanics, very likely you will not use analytical equations. You will rather use a numerical equation. And a numerical equation would mean just a numerical solution for this problem. It's the same as your reservoir simulator, right? It's a numerical solution for that equation over there. And here we're going to see there is a method which is called finite differences. And we're going to use that. We're going to have a homework. It's actually a laboratory assignment that we're going to use the same simulator that you use for reservoir engineering, CMG, to also run a mechanics problem. And there's also another solution for this, which is called the finite element method. And there are some hybrid methods also for solving these equations. But remember that when we're solving these equations, we're going to be solving that, or these kind of problems, we're going to be solving that equation. Okay? If we use this, we're going to be able to solve problems of stresses around fractures. If I had a cross section here, we'll be able to solve stresses around a wellbore. And even if you have a deviated wellbore over here, we'll be able to solve stresses around that deviated wellbore. All of that will be with that equation. Okay. All right, guys. I always get to this point in which I run out of time, and I'd like to talk next about real rocks. I have bad news for you. All this elasticity formulation we have worked on so far is actually very limited, and it doesn't work very well all the times, even for hydraulic fracturing. So you need some other solutions or some other models in order to approach the rock behavior better. And And that's when we're going to talk about real rocks, okay? We're not going to just leave some blank space in your notes. We're going to talk about anisotropy. We're going to talk about elastoplasticity. And we're going to talk about viscoelasticity, and to see what is the influence of those in real rocks, okay? We're going to do that on Tuesday, but for now we're going to skip it because I want to talk about what you have to do on Monday and Tuesday for your laboratory. Remember, you have a lab next week, okay? So don't miss it. And for that, you're going to do a test of what is called tensile strength. And now we're moving to a new chapter that I'm working on. I'm going to upload very soon. Failure of rocks. And the first one is tensile strength. How do you measure tensile strength? Or what is tensile strength? Tensile strength is the maximum stress that a solid can resist under tension, right? So if you apply tensile stresses, the maximum stress is going to be that tensile strength. Let's plot that in a strain stress diagram. And let's say that we have a, number one, we have a steel rod. And you're going to pull with stress sigma from the ends. And what would you expect to see over here? Is the steel going to deform while you pull from it? Yes, right? The steel deforms. The Young modulus is much higher than sometimes than those of rocks, but it does deform. So if you were to pull from this steel bar, is it going to deform? Notice that we're going to honor our convention of stresses. And if we have tensile stresses or tensile strains, they should be negative. So for the case of the steel, you might pull and it's going to be a negative stress, a negative strain, and you can pull very hard till it breaks. Many times steels, they have like a sort of flat region, and then they increase, and then they actually break. And when you get to this value over here, this is what is called the yield stress, and this is what is called the tensile strength. They are not the same, okay? I don't want to make a lot of emphasis on this right now, but we'll do later on. But the value we're interested in is the tensile strength, the maximum stress the material can support under tension. However, we cannot do the same test for rocks. We cannot do that because if you had a piece of rock, say like this, and you wanted to pull from the sides, you would have either to put some sort of epoxy and then to probably put the screw over there and pull from here, or alternatively you could get some sort of jaws here on the side to grab the rock and pull. But actually that doesn't work very well, because if you're here, if your epoxy is not strong enough, that's not going to resist it's going to be, if this one is smaller than the strength of the rock, it's going to fail here, right? So it doesn't make much sense to do that. Or if you apply a very high stress to grab the rock, you may break the rock here. And that's not going to work either. So you're not going to be able to, ideally, to test the true strength of the rock, which you want it to break at the middle. And another solution for this is that you say, okay, I'm not going to put the glue, I'm not going to use some jaws around here in order to grab this. I'm going to machine the rock to a shape that I can put here a sort of a steel enclosure that takes the shape of that, and now I can pull from that. But the problem with this is that you cannot really machine rock. It's not very easy to machine rock. You can machine steel, you can machine aluminum, you could more or less shape wood, but rocks are sometimes very fragile, and they have a low tensile strength, so you're not going to be able to do that. Let's assume for a moment that we are able to do this. If you were to measure the tensile strength of the rock, it's going to be much smaller than the tensile strength of steel, and also is going to fall very quickly into something which is called a brittle failure. But you could do it, right? You could measure that tensile strength over there. But this is not what you're going to do in the lab. You could do it, okay? If you could machine the rock nicely like this, if you were sculpting the rock, with a chisel and take, a day to do that, you could do that. But you cannot do that with all types of rock. So instead of that, what you're going to do is an alternative test, which is called the Brazilian test. In the Brazilian test, I don't know why this is called Brazilian, but it's called Brazilian test. Instead of subjecting a rock to tension directly, you subject the rock to compression, but you take advantage of the shape of the rock. You make a rock which is cylindrical. So this is the rock. I'm going to draw it here in 3 dimensions. And from the side, you apply the load exactly in the middle on the top. And probably here you will have a base. And if you analyze the state of stress here in the middle, and you use this one application of, where's that equation?